In the last video, we were able to draw the Lewis structure for something with a double bond, and this was because it didn't have enough electrons for every atom to have lone pairs all the way up to 8 electrons around each atom. But if we are short 4 electrons, we're going to have to include either a triple bond or 2 double bonds. So in this structure with N2, we're going to see that instance where we will be short by 4 electrons and require a triple bond. So in N2 is what we would call a diatomic element, because nitrogen is a gas made only of its own substance, nitrogen, but it doesn't exist as just N in nature. It's always bonded to another nitrogen atom. There are 7 diatomic elements that you'll find on the back of your periodic tables while you're in class to always remember which ones don't exist by themselves. But nitrogen, because it is bonded to itself and they're both nonmetal atoms, forms covalent bonds, and we can draw its Lewis structure, and we will see what happens with the electrons for nitrogen gas. Each atom of nitrogen has 5 valence electrons according to our periodic table, because it is in group 5. And so we can do what we did before, which is step 1, we draw the skeleton structure, which if we only have 2 atoms will be a nitrogen attached to another nitrogen. And we can tally up our electrons, so our valence electrons. So each one will have 5 electrons, so that means that we'll have from nitrogen, we're contributing 5 electrons each times 2 atoms, gives us a total of 10 electrons to work with. So, with those 10 electrons, so far in our first bond, we have used a total of 2 electrons, because every bond has 2 electrons. So that means out of our initial 10, so far we've already put 2 electrons onto our structure. So we can subtract those 2 and see that we have 8 electrons left. Okay. So let's evaluate how many each atom needs to get up to 8. So each nitrogen right now has only 2 electrons by it. So each nitrogen would need 6 more electrons in order to go all the way up to 8. Right? So it has to needs 6 to make 8, right? Now in this case, if we have 2 atoms, so 2 nitrogen atoms, and each needs 6 electrons, that's a total of 12 needed. We only have 8 electrons left. So that means that we are short by 4 electrons. Okay, so remember, if we are short by 4 electrons, generally we're going to need a triple bond, or you can think of this as 2 double bonds, and maybe in another structure. Okay, but in this one, we only have 2 atoms, so we can't really make 2 double bonds between different atoms. We can only really make a triple bond between our 3 atoms. So let's go ahead and place a triple bond here. And when we do that, that used up 4 more electrons. So we can subtract 4. We've got 4 left. All right, so let's reevaluate the situation. Now, each nitrogen has 2, 4, 6 electrons by it. So has 6, need 2 to get up to 8. All right. So if each one is going to need 2, so times 2 nitrogens, that's going to mean we need 4 electrons. And ta-da, we've got 4 electrons left. So each one we will give the 2 that it needs by putting a lone pair, just like always, distributing the rest of the electrons as lone pairs. And so this would be the Lewis structure for nitrogen gas. It's a little more complicated than it sounds like it would be, since it's just 2 atoms. But this is why keeping track of your electrons is so important. I know that can be a lot, but you have to think of it step by step, and it's going to take some practice to get good at it. All right, So let us look at these three molecules here because we want to talk about single, double, and triple bonds here. All right, so just like what we did before, CH4, every carbon has 4 valence electrons, every hydrogen has 1 valence electron, and so we can make a single bond between our 4 hydrogens and our 1 carbon atom, and that will mean that now we've used up all 8 of the valence electrons that are contributed by carbon and hydrogen. Okay, so 4 come from hydrogen, 4 come from carbon, and now we have 8 electrons. So carbon has 8 around it, and all of our hydrogens just have 2, just like they want to have since they're in the first energy level. So this is the structure for methane. Okay, all of these bonds are single bonds, and single bonds are what we can call a sigma bond. Sigma means that it is the bond holding the atoms together. So if you hear the term sigma bond, it means the bond that's holding the atoms together. Now, sigma bonds are also involved when we have double bonds and triple bonds, but we're going to add on another bond in that place called a pi bond, which is really just like extra electrons that are being shared between the atoms, which is why it becomes double or triple. So let's look at an example with a double bond. In this structure, we have carbon is our least, well, it's more electronegative than hydrogen, but because it's not hydrogen, we can put carbon in the center, because remember, hydrogen will never go in the center. So our 2 carbons can be thought of as our center of our molecule, but then we have 4 hydrogens, and so that means 2 hydrogens are going to go on each carbon to make it as symmetrical as possible, because that's really something that molecules like to do. They like to be symmetrical as possible. Okay. So right now we have our skeleton structure, and let's tally up all of our electrons. Okay, as we've said before, carbon contributes 4. So if we have carbon, we have 4 valence electrons from 1 carbon and 2 carbons, so that's a total of 8. And from hydrogen, hydrogen has 1 valence electron times 4 hydrogens. That gives us 4 electrons, so that's a total of 12. So far we've used 2, 4, 6, 8, 10. So we can subtract 10 from here, and that means we've got 2 electrons left. Okay. So now we need to see which atoms need more electrons. All of our hydrogens are fine because they only need 2 electrons, and that bond is the 2 electrons that they need. But our carbons only have 3 bonds to them, and that means 6 electrons around each carbon. So each carbon is going to need 2 more electrons, which, if we have 2 atoms needing 2 more electrons, that's a total of 4 more electrons. We've only got 2 left to work with, so we are short by 2 electrons for our whole molecule, so that means we are going to have to include a double bond. The double bond should go between the atoms that need more electrons, so carbon and carbon. This is called ethene, and this has 1 sigma bond connecting the 2 atoms and 1 pi bond, the extra shared electrons. Okay, so in a double bond, you have 1 sigma and 1 pi. Pi is extra shared electrons. Okay. I don't know why it's not writing that. Okay. All right, now we get up to the last one here, C2H2. Now this one is similar to this one except it has 2 less hydrogens. So that means we're going to have carbons and 1 hydrogen attached to each carbon. Okay, so now if we had 2 carbons and that gave us 8, from carbon again we're going to get 8 valence electrons. And from hydrogen this time we only have 2 hydrogens, so 2 times 1, 2. Alright, so we've got a total of 10 electrons to work with. And we've used 2, 4, 6 so far. So we've got 4 left. Okay? Now let's evaluate each carbon here. Carbon can make a total of 4 bonds, and this one's only making 2 bonds. So that means 4 electrons are coming to each carbon right now, and it needs 4 more to get to 8. Alright, so if there's needed 4 here, so we need 4 on each one. That's a total of 8 more electrons that we need, but we only have 4. So in this case, we're short by 4 electrons because we only have enough to make one of the carbons happy. So when we're short by 4, that means we're going to need two double bonds or a triple bond. Now, we can't make a double bond between a hydrogen and a carbon because hydrogen would have too many electrons then. So our only option is to put a triple bond between our 2 carbons. And now, neither carbon needs any more electrons. Alright, and we've used up our last 4, 2, 4. Oops, that looks like a lone pair, it's not. We've used up our last 4 electrons in making that triple bond. So we've got 0 left, just like we want. Alright, so this has 1 bond that we use to connect the atoms, and now it actually has 2 pi bonds. So a triple bond is composed of 1 sigma and 2 pi. Remember, these pi are the extra electrons that are used to satisfy the octets of the atoms. Okay? Alright. Let's briefly talk about polarity and molecular shape because we're not going to get too much into this, but if you remember, a bond can be polar, meaning that the electrons are closer to one atom than the other, if there's a difference in electronegativity. So if we remember, chlorine has a high electronegativity, whereas hydrogen has a very small electronegativity. This means that chlorine pulls the electrons towards itself, and this is kind of the arrow you would see to describe that more of the electron density, as we say, is pulled towards the chlorine. So we use this arrow with a little line through it to show that. Okay, so it's polar in the direction of where the chlorine is. But however, when we have 2 of the same atom, they have an equal electronegativity. Okay? Because they're the same element, so they have the same amount of electronegativity. So neither one of them can pull the electrons closer to itself. They're right in the middle, and they just kind of move around there in the middle between the 2 atoms. Now, that's about how bonds can be polar, but if we think about entire molecules, that molecule has a whole bunch of bonds in it, and some of those bonds could be polar, and other ones could be less polar. But an example is carbon tetrachloride. This is a carbon with 4 chlorines on it. And, you know, depending on where the chlorines are, the angles could cause the polar bonds, where they're each pulling away from the carbon. Okay, the electrons are closer to chlorine because chlorine is closer to the top right of the periodic table. Depending on how these atoms are arranged around the center, the whole molecule could have an overall polarity in one direction. But this molecule is very symmetrical because all 4 of the groups coming off of our carbon are the same element. So overall, they're all pulling in the opposite direction, just like tug of war. And you know that when you play tug of war, if you have a knot in the center of the rope and the 2 people pulling on either side are equally as strong, that knot is not moving in any direction. You can think of it like that. So the electrons are all being pulled equally, so therefore this molecule is non-polar overall. Each of the bonds is polar, but the whole thing is not having the electrons on one side more than any other side. Okay? So that's how the shape can be important. Now if we look at carbon monochloride, like in this molecule right here, CH3Cl, we've got only 1 chlorine atom, so it's right here. And so this bond is really polar. These bonds are a little bit polar because it's a carbon to hydrogen bond, but the carbon is a little more electronegative than each of the hydrogens.